In this biomedical instrumentation lecture, we'll discuss BioMEMS and Microfluidics. So BioMEMS and Microfluidics stemmed from advances in miniaturizing electronics. So why do we care about small electronics? Well, famously, Richard Feynman in the 1959 meeting of the American Physical Society said, "There's plenty of room at the bottom," meaning that there's plenty of room for technical advances on the small scale of things. Small devices means that you're going to have less heat and greater power efficiency. So here's, for example, is an example of a vacuum tube versus a transistor around 1950. They perform the same function, but you can see that the transistor incorporated an advance in small sizes. And people were interested in getting down to small sizes in electronics because at the time, wire distances between transistors made responses too slow. It was hard to build fast computers and fast other devices when you had long wire distances between the different transistors. However, if you pack the transistors on top of each other to try to get them closer together and save space, they get too hot. So one solution that you could come up with is, since all the transistors were built out of silicon doped with N and P type materials, as we talked about with diodes, the question is, could they just be made on a single block of silicon altogether? The second solution was to ask whether the interconnecting wires between the different transistors could also be laid down on the silicon block. And so this was famously attributed to Jack Kilby, who was a new employee at Texas Instruments in 1958. Then Robert Noyce came along and asked, well, instead of laying down wires onto this chip substrate, could you just lay down an entire metal layer and just erode it into the wires? Robert Noyce then went on to found Intel. So then you can approach this manufacturing in three different ways. You can lay down layer by layer and then etch away the undesired parts that you don't want to get the patterns that you do want. Then you can fill the spaces in between the remnants that you haven't eroded away with different materials, or you can change the material by injecting appropriate doping materials such as N-type or P-type doping to make diodes or transistors. So here's a basic high-level view of the pattern transfer process. So we have a silicon substrate here illustrated in gray, on top of which we coat the material that we want to etch a pattern into, be whatever it might be. On top of that, we coat in patterns this photoresist pattern that we'll talk more about later, but that is how we actually apply a pattern onto the substrate that we want to generate. Then we can etch the film using the photoresist as a mask. So the idea is that the photoresist protects the material underneath it that you don't want to etch away. And you can get positive or negative photoresist, as we'll talk about later. And then but whatever is in between will be etched away. Then you remove the photoresist and you're left with a pattern of the material that you actually wanted. And there are lots of advantages to integrated circuits. So while they have a very high startup cost to build them, you have a much lower unit cost than discrete components. That is, it takes a lot of money to make the first one, but after that, the cost diminishes dramatically. You get a much greater uniformity of performance and much tighter manufacturing tolerances. You get much lower weight and greater functionality density, that is, the amount of functionality that can be packed into a small area. So, for example, NASA and missile defense folks were interested in this. In missile defense, they wanted to pack a lot of electronics into missile nose cones. And then you end up getting lower assembly costs, which translates to advantages in commercial products. That is, you can make cheaper FM modulators for TVs or radios. So the next idea was to see if they could combine mechanical systems onto these chips. And when they do that, you get what's called MEMS, or micro-electromechanical systems. These are devices that are fabricated using batch integrated circuit fabrication processes. They are systems that can then sense, control, and actuate on the micro scale, and they function individually, or they can function individually or in arrays to generate effects on the macro scale. So, for example, displays can be made this way out of many, many little devices that each represent a pixel or etc. And then biomedical applications of MEMS then give us BioMEMS. And so MEMS really combined the skills of mechanical engineers and electrical engineers to advance this leap forward in functionality on the small scale. So here's a cool old ad showing all the different ways that MEMS devices, or these micromachine transducers, can be integrated to improve safety and operation of automobiles. So I think the very first application that was widely used was accelerometers for airbags. But also there are applications such as tire pressure sensors or silicon nozzles for fuel injection inside the engine, or fuel pressure sensors, microphones for noise cancellations, side impact sensors, another accelerometer application, fuel sensors, all kinds of different things. And when we replace the car with the body, we get biomedical applications of MEMS devices, or BioMEMS. So there's lots of different applications for MEMS in the body. So here's a blown-up example of a blood pressure sensor, muscle stimulator here shown, a cortical probes, as we talked about earlier, are a big application of this, pacemakers, bladder stimulators, all kinds of different things. So BioMEMS for biomedical and biotechnological applications require basic foundations in understanding of biophysics, biochemistry, solid-state devices, and polymer engineering, which when you integrate together, you get the biomedical engineers that you guys are. And again, the advantages of small devices are just their compactness, their small size, they're fast, devices become fast, they require low power and can become wearable, and then they can have very simple interconnects. Here's Moore's law, which illustrates the advance of the number of transistors that can be packed into a space, into a chip, and it was predicted by Moore, I believe it was a Stanford professor, who said that the number of transistor would double every 2 years from 1970 on. And we saw that this really held up well into the mid-2000s. And now it seems to it's starting to be displaced perhaps by a law governing power efficiency. And similar to semiconductor fabrication processes, microfabrication processes consist of patterning and depositing multiple layers. So what you do is you deposit a layer of the material you want to form into a piece, and then you pattern that layer with photolithography, and you remove the unwanted portions using various techniques that we'll talk about. Microfluidic devices provide all of the possible required analyses for a given problem that can be done on a single chip. There's lots of different advantages to them. So for example, you get fine control of cell surroundings. That is, you can set up gradients of a given nutrient, for example, and see how that impacts the cells over a small space. Chemical reactions become more efficient as molecules cannot diffuse away. You can build many parallel units for the same approximately the same low cost of a single unit just as easily. You get very predictable fluid behavior, which we'll get into more detail soon. And then you can do obtain detailed physiochemical knowledge of the entire system. So now let's get into some details about the manufacturing processes. So if we want to etch something, first we have to get it onto the substrate in the first place. And there's three basic approaches to do this. There are spin-on films, physical vapor deposition processes, and chemical vapor deposition processes, which we'll talk about in a little bit. Spin-on films include substances like polyamide, photoresist, spin-on glass, and PDMS. Polyamide is like a rubbery material that can be coated on top of like copper to make like flexible laptop displays. And PDMS, you probably all know, is the material used to make microfluidic devices. Physical vapor deposition is the process of evaporating a substance from some evaporation source, then which creates a flux of that evaporant, then onto the substrate that you're trying to coat with that. And it's performed under high vacuum conditions. So here's an example of a chemical or physical vapor deposition system. Here is called an electron beam evaporation system. So in this device, you have this electron source, which is like this heated filament that then shoots electrons around onto the face of the evaporant metal that you want to evaporate and get onto your substrate, onto your silicon substrate, and it's catapulted up there by a magnetic field that's sitting right here that pulls it up and makes it hit the metal piece, and then this metal vapor is knocked off, evaporated. And then it goes on to be deposited on the substrate. Another thin film deposition technique is sputtering. In sputtering, you have this target electrode here, which is made of the material that you want to deposit onto the substrate, and you put a DC voltage or RF voltage between that target electrode and a plasma that then knocks ions out of the plasma and into the target electrode, which then consequently knocks the material off of the electrode and over onto the substrate. And so this is useful in particular for compounds and mixtures that are not amenable to evaporation, such as titanium oxide and aluminum oxide. This is also the process by which the silver material is for CDs, DVDs, and Blu-ray discs is deposited. An interesting fact about sputtering is that it is the process by which space weathering happens. Chemical vapor deposition is another technique, and basically this is an overview of how these different chemical deposition techniques work. What you do is you have this gas phase precursor of the element to be deposited. It then reacts or decomposes over top of the substrate to produce the desired composite material that then will fall and be deposited on the substrate. It's done with ventilation to remove the volatile byproducts. And it's very much like the way that you have formation of soot on a cool object that you put in a flame. So you're just flipping the heat, which thing is hot and which is cold. This is also, it turns out, this is the way that synthetic diamonds are made. And this particular illustration is showing how silicon dioxide is deposited. So we know how to get materials onto a substrate. Now how do we get it off? So photolithography is the most widely used way to do that, and it's a subtractive patterning process in which material is selectively removed. So what you do is you coat your wafer with photoresist. This is an example here of a spin coating. And then you soft bake it to harden the photoresist. You align it with a mask, and then you expose it to ultraviolet light. Then you do another post-exposure bake. You develop it using some chemical technique, some chemical wash. You do what's called a hard bake, and then you, of course, develop and inspect it. So here's the process by which we get photoresist onto the substrate. So you have the photoresist. This is showing a machine that is dropping photoresist onto a substrate which is spinning. It spreads out with a uniform thickness on top of the wafer that is being coated, and then it goes through a soft bake to dry or partially harden the photoresist. Then it is exposed to ultraviolet light according to some mask. And after that exposure, a wet chemical development is applied, and depending on whether we've applied a negative or a positive photoresist, we'll either have the exposed photoresist left over or the unexposed photoresist left over. So that is, positive photoresist becomes soluble when exposed to light, whereas negative photoresist becomes insoluble when it is exposed to light. So then once we've got the photoresist patterned on there, then we can start to deposit the material that we actually want to put on the substrate. So we do this blanket deposition on top of the material that we want to deposit on top of the photoresist. Then we swell it using some kind of chemical solvent, which makes it easier then to remove. And what's left over is just the material that we wanted to deposit. If instead of removing the material that is on top of the photoresist, we instead want to remove the material that is not on top of the photoresist, then we can use etching. And so etching, a chemical etch, is an isotropic procedure in which you get these somewhat rounded walls. You get some undercut underneath the photoresist, which is illustrated in red here, and then the material we're trying to deposit is illustrated in blue. The substrate is dark blue. And when you apply this chemical etch, like a solvent that you apply, then you get these somewhat rounded walls here. You can also do silicon etching techniques, which gives you anisotropic etching, and thus allows you to go a little bit deeper to get higher aspect ratios. Here, you have a certain direction in which you have the fastest removal of material. And the etch rates depend on the crystal direction. So in this case, the etch rate in this vertical 100 direction is much higher than in the lateral directions. Potassium hydroxide chemical etch is a wet silicon etch is a wet etchant that's used for crystal-oriented anisotropic etching of monosilicon. Thermal oxide or LPCVD nitride masks are commonly used to stop the etch. So here's how we can adapt this process to make like a microfluidic type channel in glass. It's a very similar process in which we take the substrate, a piece of glass, we coat it with photoresist in blue here, then we apply photolithography via this mask where the mask contains the pattern of channels that we want to imprint into the glass. After photolithography, we deposit chromium on top of it and then lift off the metal, and then we can use the metal deposited as another mask that defines where the channels will be etched into the glass. So we then do the etching of the glass to form the channels, the fluidic channels. We drill some access holes in a top wafer and then plop that on top. And then we can bond it at a high temperature, the two pieces of glass together at a high temperature to create a single piece. The nice things about this are that it's compatible with silicon fabrication. It's transparent, so you can do optical techniques with it. It's insulating. You have low autofluorescence of the glass, and it's cheap. It's possibly cheaper than silicon. At the same time, it's an amorphous material. That is, it can change shape over time and with different temperatures, and it's incompatible with high temperatures. Another way to remove material off the surface of the substrate is to use ion beam assisted etching. This is where we have an ion beam that is where ions come from these noble gases that is aimed at the substrate, and so you can tilt and rotate the substrate then to expose different parts of it to the beam. Really nice thing about this is that it gives you no undercut as with the chemical etches and allows you to have high aspect ratios. By aspect ratio, I mean the ratio of height to width of your features that you etch. Another way to get tall, deep structures or high aspect ratios is to use a special kind of epoxy called SU8 Photoepoxy. This is a special kind of photoresist that has its tail end of its absorbance is right in the UV spectrum, which is what we use for photolithography, and so it has a high transparency and it gives low secondary scattering. That means it doesn't scatter too many photons out from itself, and so most of the photons that actually get into the photoresist are the primary photons that came from the light source directly. That gives you large exposure depths, which then translate into large aspect ratios. So this was really fundamental because it allows us now to do up to 1 millimeter thick features, whereas most photoresists cannot do much better than 20 microns, which was a huge problem for microfluidics at the outset, and then until IBM invented this SU8 photoepoxy in the late 90s. It is a negative photoresist, but it's a photocurable epoxy. And let's see, the UV light what happens is that UV light causes this photochemical release of an acid, which forms this soluble polyester network, and it's really preferred for microfluidics today. And it's possible with this stuff to get 10-to-1 height to width ratios. So a fundamental advance that was enabling for microfluidics was the introduction of PDMS, or photosensitive polydimethylsiloxane. It was pioneered by this guy George M. Whitesides at Harvard, who incidentally started on NMR and has the highest H index of any living chemist. It's very cheap stuff, and so it's a very enabling technology. It's what's really great is that it's a flexible photosensitive material that can be photosensitized for etching or curing. And so here's one way that we can use it. So you can have a negative photoresist spread on a silicon wafer, and then you expose it with a mask of the channels that you want. Expose that photoresist with the mask of the channels that you want, which then gives you this raised pattern of the channels after you develop that photoresist. Then you can cast the PDMS onto it, and you'll get an imprint of the channels that you want in the PDMS. You can pull it off then and put another piece of PDMS or a piece of glass underneath it, drill some holes to get some buffer, some access points and reservoirs, and you've got the device. And so here's another view of this. Let's say we start out with this mask design of the channels that we want to impose on the PDMS. Then we deposit this positive photoresist on the silicon wafer that is the substrate. It's not actually going to be part of the final device though. Then we expose and develop the photoresist. That's a little bit hard to see here, but you have these black channels here that are illustrated. Then you cast the PDMS on top of that silicon wafer with the channels on top of it, the imprints of the channels on top of it. You cure the PDMS and remove the substrate, and you're left with the channel imprint that you want. And the cool thing is that you can build these devices up in layers, and so you can actually make a fluidics layer that actually contains the analytes that you're interested in. You can make a control layer that is equivalent to a set of valves. So in this particular device, we have these valves here that we're going to pump full of water, pump full of fluid that will, if you do them in a sequential manner, pump them full and release them in a sequential manner. Then you'll push fluid along in the fluidics layers, and you can control these two inputs separately. Then, and then we layer these two on top of each other to get the structure of the device that we want. And here's this device in particular. So this is a picture of, I think this is one of Franz Bodenbacher's devices. He calls it the nanophysio. And these valves here work like a peristaltic pump where you push fluid into each one in sequence, and that moves fluid along into the chamber, and you can do it in the opposite direction to pull fluid out of the chamber. This is the sensing volume here, and then you have these different waste channels here. And the idea of this device is that it provides a high bandwidth detection of cellular activity with control of the extracellular environment. It enables then fluorescence imaging and electrochemical measurements using microelectrode arrays that it can also be placed along the bottom of it, the channels. Okay, so now let's go back and talk about the microfabrication process and how we can get some suspended structures. So remember that the microfabrication process is this iterative procedure of depositing a layer, patterning it with photolithography, and then removing the unwanted portions, and just doing this over and over and over again until we build up the device that we want. And we can build this kind of suspended structures that we need for MEMS devices by depositing first an insulating layer, then depositing and sacrificing a sacrificial layer that we know we're going to get rid of later, but that the material that we want to have suspended will sit on top of. Then we deposit and pattern the structural layer that forms the suspended structure, and then we selectively etch away the sacrificial layer, leaving the suspended structure behind. So here's an example of a MEMS gas flow sensor that works by the same mechanism as the hot wire anemometer that we talked about earlier in class, where we have the suspended silicon membrane that is heated up by this heater, and it's going to be exposed to this air or gas flow through it that will remove heat from it, and will measure the resistance actively as that flow is happening. And to make high-precision gas flow measurements, we're going to have good sensor sensitivity and very good linearity over the range of flows that we care about. We can also think about the sensor geometry in controlling the sensitivity and its dimensions. So, for example, the flow through it is going to be proportional to, I think this should be r to the fourth actually, but it's going to be proportional to a power of the radius. So that is going to control considerably the sensitivity of the device. But there are a lot of advantages to a MEMS-based gas flow sensor like this. So it will have very fast response times because it's such a small device that it will be easy to remove heat from it. It will have very low power consumption, again because it's small, and will allow you to measure very small flows with high precision and accuracy.